Welcome to this gentle exploration of perhaps the most profound mystery our universe holds close to its heart. Tonight, we drift into the quiet contemplation of something that surrounds us at every moment, yet remains forever beyond the reach of our eyes. In the vast theater of space, where stars perform their ancient dance and galaxies spiral through the cosmic dark, there exists a presence so subtle, so pervasive, that we have only recently begun to whisper its name: dark matter. Picture, if you will, the universe as a grand symphony hall, where every note we can hear represents the familiar matter that makes up stars, planets, and ourselves. Yet this beautiful music we perceive, every twinkling star, every swirling nebula, every planet that catches the light of its sun, represents merely 15% of the orchestra. The remaining 85% plays in frequencies we cannot detect, creating harmonies we cannot hear, yet without which the entire cosmic composition would collapse into silence. There is something both humbling and beautiful about this realization. As you rest here tonight, dark matter particles are streaming through your body, through these walls, through the earth itself, at speeds that would make light envious. They pass through us like cosmic ghosts, interacting so weakly with ordinary matter that trillions upon trillions flow through every square inch of space, each second, leaving barely a trace of their passage. Yet paradoxically, it is precisely this ghostly, almost ephemeral quality that makes dark matter the most influential architect in our universe. In the quiet depths of space, where human eyes have never gazed, and telescopes strain to capture the faintest whispers of light, dark matter weaves the very fabric upon which all visible creation rests. It is the invisible hand that guides galaxies in their cosmic waltz, the silent sculptor that carved the large-scale structure of everything we see. Without its gentle but persistent gravitational embrace, the atoms that eventually became stars would never have found each other across the expanding void. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of these elements were forged in stellar furnaces that could only exist because dark matter first gathered the cosmic ingredients together in patient, invisible hands. This hidden majority of our universe speaks to something profoundly mysterious about the nature of reality itself. We live our daily lives surrounded by what we can touch, see, and measure, creating an illusion of completeness in our understanding. Yet the cosmos gently reminds us that the seen is always dwarfed by the unseen, the known by the unknown. It is as if we have been reading a magnificent novel, completely absorbed in its beauty and complexity, only to discover that we have been experiencing merely the footnotes, the main text written in an invisible ink that we are only now learning to detect. The story of dark matter is ultimately a story about the limits and the power of human curiosity. For billions of years, this cosmic majority remained completely hidden from every living thing that ever gazed upward at the night sky. Ancient astronomers mapped the movements of planets with exquisite precision, yet remained entirely unaware of the dark ocean in which all celestial bodies swim. Even today, with our most sophisticated instruments and our deepest theoretical understanding, dark matter continues to guard its secrets with an almost playful elusiveness. Yet this mystery does not discourage us. It enchants us. There is something profoundly calming about acknowledging that the universe still holds wonders beyond our current comprehension. In a world where we often feel we have mapped and measured everything, dark matter stands as a gentle reminder that reality is far stranger, far more mysterious, and far more beautiful than our ancestors ever dared to imagine. As we embark on this nocturnal journey through the invisible cosmos, we will discover that dark matter is not merely an abstract scientific concept, but the very foundation upon which our existence rests. It is the quiet force that allowed galaxies to form, stars to ignite, and ultimately, life to emerge in pockets of warmth and light scattered throughout the cosmic dark. In learning about this hidden realm, we learn about ourselves and our place in a universe that is far more mysterious and wonderful than meets the eye. In the gentle flow of scientific discovery, there are moments when the universe whispers something so unexpected, so contrary to our carefully constructed understanding, that it changes everything. Such a moment came in the 1970s, carried on the patient observations of a remarkable astronomer named Vera Rubin, whose work would forever alter our perception of the cosmic order. Picture Vera, night after night, at the eyepiece of telescopes, studying the graceful spiral arms of distant galaxies. These cosmic pinwheels, scattered like flowers across the dark garden of space, had long been admired for their beauty. But Rubin was interested in something more fundamental. She wanted to understand how they moved. What she discovered was so surprising that it would challenge centuries of our understanding about gravity and motion in the cosmos. To appreciate the magnitude of her discovery, imagine a figure skater performing a gentle spin. As she pulls her arms closer to her body, she spins faster. This is the dance of angular momentum that governs rotating systems throughout the universe. Now picture our solar system. Mercury, closest to the Sun, races around its orbit at nearly 50 kilometers per second, while distant Neptune moves at a leisurely 5 kilometers per second. This makes perfect sense. The closer you are to the gravitational center, the faster you must move to maintain your orbit. Rubin expected to find this same pattern when she measured how fast stars orbited within spiral galaxies. The stars near the galactic center should be moving quickly, while those in the outer regions should be moving more slowly, following the same gravitational choreography that governs planets around the Sun. But as her measurements accumulated, a mysterious pattern emerged that defied all expectations. There is something almost musical about the way Rubin described her discovery. The stars in the outer regions of galaxies were moving far too fast. So fast that, according to everything we understood about gravity, they should have been flung out into the cosmic void like stones released from a slingshot. Yet, there they were, serenely following their orbital paths as if held by some invisible gravitational hand. Night after night, galaxy after galaxy, the same impossible pattern emerged. The rotation curves, graphs that showed how orbital velocity changed with distance from the galactic center, refused to follow the expected downward slope. Instead, they remained stubbornly flat, indicating that stars in the galactic suburbs were moving just as fast as those closer to the center. It was as if the figure skater could extend her arms without slowing down, defying the fundamental laws of physics. The implications were staggering. Either our understanding of gravity, tested and confirmed countless times since Newton first formulated his laws, was incomplete, or there was far more matter in these galaxies than anyone had ever imagined. The visible stars, glowing gas clouds, and stellar remnants that we could detect with our telescopes represented only a tiny fraction of what was actually there. Something invisible, something that interacted gravitationally but remained completely hidden from all forms of electromagnetic radiation, had to be present in enormous quantities. As we drift deeper into this mystery, we can almost feel the excitement and bewilderment that must have filled those observatories in the 1970s. Here was evidence that the cosmos was not what it seemed, that every galaxy existed within a vast halo of invisible matter, like a soap bubble floating in an unseen ocean. The stars we could see were merely the lighthouse beacons, marking the presence of something much larger and more mysterious. Rubin's discovery was all the more remarkable because it revealed the presence of the invisible through the behavior of the visible. The dark matter could not be seen directly, but its gravitational influence was written in the motions of every star in every galaxy she studied. It was like detecting the presence of a massive, invisible person in a room by watching how others walked around them. The dark matter revealed itself through the cosmic choreography it orchestrated. Yet this revelation brought as many questions as answers. If most of the matter in the universe was invisible, what was it made of? Why didn't it interact with light? How had it remained hidden for so long? These questions would drive decades of subsequent research, launching an entirely new branch of astronomy dedicated to understanding the invisible majority of our universe. The beauty of Rubin's work lies not just in its scientific importance, but in its demonstration of how patient observation can unveil the deepest secrets of nature. By simply measuring the speeds of stars with extraordinary care and precision, she opened a window into a hidden realm that shapes everything we see. Her galaxies became cosmic Rosetta Stones, their stellar motions spelling out the presence of something wonderful and mysterious that had been there all along, waiting for someone with the right eyes and the right questions to notice its subtle influence on the dance of stars. In the quiet depths of space, billions of years before the first star ever kindled its nuclear fire, something extraordinary was already at work. Long before there was light to illuminate the cosmic darkness, an invisible architecture was taking shape, a vast, intricate scaffolding upon which all future beauty would be built. This is the story of how dark matter became the master architect of everything we see in the universe today. Imagine, if you will, the universe in its infancy, a time when it was nothing more than an almost perfectly smooth ocean of particles and energy, with only the faintest ripples disturbing its tranquil surface. These tiny fluctuations, imprinted in the cosmic microwave background radiation that we can still detect today, were like the gentlest of breezes on an otherwise calm lake. Yet from these whisper-soft variations would grow the grandest structures in the cosmos: galaxies, galaxy clusters, and the magnificent web-like network that connects them across billions of light years. Dark matter, with its ghostly ability to feel gravity while remaining invisible to light, began its patient work almost immediately after the Big Bang. Unlike ordinary matter, which was still locked in a fierce battle with photons, a cosmic dance of creation and annihilation that kept it hot and turbulent, dark matter could begin to clump and gather without interference. It was like having an artist who could work in complete silence while everyone else was distracted by noise. There is something almost musical about how this cosmic architecture took shape. Dark matter flowed through the expanding universe like a slow, majestic symphony, its gravitational harmonics drawing together the building blocks of future galaxies. Where dark matter gathered, it created gravitational wells, invisible valleys in the fabric of space-time that would eventually become the birthplaces of stars and galaxies. As millions, then hundreds of millions of years passed, these dark matter concentrations grew stronger and more complex. They formed what astronomers now call the cosmic web, a vast network of filaments stretching across the observable universe, connecting node to node like neurons in some cosmic brain. At the intersections of these dark filaments, where multiple streams of dark matter converged, the gravitational attraction became strong enough to begin pulling in the ordinary matter that would eventually light up as stars. The beauty of this process lies in its gentle persistence. Dark matter didn't force the universe into its current form, it invited it. By creating regions of enhanced gravity, it provided gathering places where hydrogen and helium could slowly accumulate. These cosmic meeting grounds became the nurseries where the first stars would eventually ignite their nuclear fires, illuminating the dark matter scaffolding that had been patiently waiting for this moment. Meanwhile, across the vast expanse of cosmic time, this same invisible architecture was working on scales both large and small. Individual galaxies formed within dark matter halos, enormous, roughly spherical concentrations of invisible matter that provided the gravitational foundation for stellar communities. Our own Milky Way exists within such a halo, a dark matter structure perhaps 10 times more massive than all the visible stars, gas, and dust it contains. Yet the story becomes even more wonderful when we consider the cosmic web as a living, breathing entity. This network of dark matter filaments is not static. It continues to evolve, with smaller structures merging into larger ones, and matter flowing along the filaments like water through an invisible circulatory system. Galaxies slide along these dark highways, occasionally colliding and merging when their paths intersect, creating even grander structures in an ongoing cosmic dance that has been unfolding for nearly 14 billion years. Perhaps the most beautiful aspect is how this invisible scaffolding enabled the eventual emergence of complexity and life. Without dark matter's patient work in the cosmic dark ages, ordinary matter would have remained too diffuse to form stars. No stars would have meant no heavy elements forged in stellar cores, no planets, and ultimately, no life. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of these elements exist because dark matter first created the gravitational stages where stars could perform their alchemical transformations. There is something profoundly calming about understanding our place within this cosmic architecture. As we rest here tonight, we are held not just by Earth's gravity, but by the gravitational embrace of our galaxy's dark matter halo, which in turn is connected to the vast web of invisible filaments stretching across the universe. We are part of a structure so grand and ancient that it challenges the very limits of imagination, yet so integrated that every atom in our bodies bears witness to its patient, creative work. The cosmic scaffolding of dark matter reminds us that sometimes the most important foundations are the ones we cannot see, like the roots of a forest that remain hidden underground while supporting the visible beauty above. Dark matter's invisible network provides the foundation upon which all cosmic beauty rests, a testament to the universe's profound wisdom in building from the unseen to create everything we can see and touch and love. In the gentle realm of scientific understanding, there is perhaps no concept quite as paradoxical as dark matter, a substance we define almost entirely by what it is not, yet which forms the backbone of everything that is. Tonight, we drift into the contemplative challenge of describing the indescribable, of understanding something that seems to exist in the spaces between our senses and instruments. What do we know about dark matter? The question itself carries a beautiful irony because our knowledge is built almost entirely on absence. The absence of light, the absence of electromagnetic interaction, the absence of any direct detection despite decades of searching. Yet from these absences, we have constructed a portrait of something extraordinary, a form of matter that participates in the cosmic dance through gravity alone, shaping the universe while remaining forever beyond the reach of our eyes. Picture, if you will, a cosmic ghost that can only be detected by its shadow. Dark matter does not emit light, which is why we call it dark. It does not absorb light, which means it cannot be warmed or cooled by stellar radiation. It does not reflect light, making it invisible to even our most sensitive mirrors and lenses. In the entire electromagnetic spectrum, from radio waves to gamma rays, encompassing all the ways we have learned to see the universe, dark matter remains perfectly, persistently transparent. Yet this ghostly quality is precisely what makes dark matter so influential. Because it interacts only through gravity, it can flow through ordinary matter as if it weren't there. Right now, as you listen to these words, dark matter particles are streaming through your body at hundreds of kilometers per second, passing through every atom, every cell, every thought, without disturbing so much as a single electron. It is matter that is present everywhere, yet touches nothing, influential, yet aloof. There is something almost Zen-like about dark matter's relationship with the universe. It shapes galaxies without being shaped by them, influences the paths of stars without being influenced by their light, and participates in the cosmic story while remaining a silent partner in the background. In a universe where ordinary matter is constantly interacting, atoms bonding and breaking, charged particles dancing with magnetic fields, photons bouncing between surfaces, dark matter maintains a kind of serene detachment, engaging only through the gentle pull of gravity. The mathematical beauty of dark matter reveals itself in the cosmic ledger. When we add up all the visible matter in the universe, every star, every planet, every cloud of gas and dust, we account for only about 5% of what must exist to explain the gravitational effects we observe. Dark matter makes up approximately 27% of the cosmic inventory, while the remaining 68% consists of something even more mysterious: dark energy, the force driving the universe's accelerating expansion. This cosmic accounting reveals something profound about the nature of reality itself, the familiar world of atoms and molecules, the periodic table that organizes all known chemistry, the electromagnetic forces that govern how matter behaves. All of this represents less than 1/20th of what exists. It is as if we have been living in a single room, of a vast mansion, completely unaware of the many floors and countless chambers that surround us. As we drift deeper into this mystery, we encounter one of the most beautiful aspects of dark matter's definition: its democratic distribution throughout space. Unlike ordinary matter, which clumps into dense stars and planets separated by mostly empty space, dark matter forms smooth, extended halos around galaxies. It fills the space between stars, creating a kind of invisible medium through which all cosmic objects move. In this sense, dark matter is more truly omnipresent than ordinary matter, creating a kind of gravitational ether that permeates all of space. The distinction between dark matter and dark energy often confuses those first encountering these concepts, and there is a poetic beauty in understanding their differences. Dark matter pulls. It is the cosmic glue that holds structures together, the invisible foundation that allows galaxies to maintain their integrity across billions of years. Dark energy pushes. It is the mysterious force that drives the accelerating expansion of space itself, working to stretch the universe and dilute all forms of matter and energy. Perhaps the most remarkable thing about our definition of dark matter is how it emerged from pure observation rather than theoretical prediction. Unlike many discoveries in physics, where theory preceded observation, dark matter announced itself through the stubborn refusal of galaxies to behave as expected. It was reality insisting that our understanding was incomplete, the universe itself teaching us about the limitations of our perception. There is something profoundly calming about accepting that the universe contains so much that we cannot directly perceive. Dark matter reminds us that reality extends far beyond the boundaries of our senses, that the unseen is not the same as the unreal. In learning to define the invisible, we learn something important about the nature of knowledge itself, that understanding does not always require direct experience, and that some of the most important truths reveal themselves only through their effects on the world we can see. In the gentle flow of scientific discovery, there are moments when a single person peers into the cosmic darkness and glimpses something that will change humanity's understanding forever. The story of dark matter begins not in the 1970s with Vera Rubin's revolutionary observations, but decades earlier in the 1930s with a Swiss-American astronomer named Fritz Zwicky, whose restless curiosity would open the first window into the invisible universe. Picture Fritz Zwicky in 1933 working at the California Institute of Technology, his attention drawn to the Coma Cluster, a magnificent collection of over 1,000 galaxies bound together by gravity, dancing their cosmic waltz some 320 million light-years from Earth. There is something almost prophetic about this moment, as Zwicky applied a technique as elegant as it was straightforward. He measured how fast the galaxies within the cluster were moving, then calculated how much matter would be needed to keep them gravitationally bound together. What Zwicky discovered was deeply unsettling. The galaxies in the Coma cluster were moving far too quickly, so quickly that the visible matter in all those 1,000 galaxies combined was nowhere near sufficient to hold the cluster together. According to his calculations, there had to be at least 10 times more matter present than anyone could actually see. In his characteristic directness, Zwicky coined a term that would echo through the decades: dunkle materie, dark matter. Yet this groundbreaking discovery was met largely with cosmic silence. The astronomical community of the 1930s was not quite ready to embrace the idea that most of the universe might be invisible. Zwicky's work was filed away like a whisper in the cosmic wind, waiting for the right moment and the right observer to give it voice. It would take nearly 40 years for the astronomical world to truly listen to what he had been trying to tell them. Meanwhile, across those intervening decades, the universe patiently held its secrets. Telescopes grew larger and more sensitive. Observational techniques became more refined, yet the mystery Zwicky had stumbled upon remained largely forgotten. It was as if the cosmos was waiting for someone with the perfect combination of technical skill and persistent curiosity to rediscover what had been hiding in plain sight all along. That someone was Vera Rubin, whose work we have already glimpsed, but to truly appreciate the magnitude of her contribution, we must understand the evolution of her observations. Rubin didn't set out to revolutionize cosmology. She began her career studying the rotation of our own galaxy, the Milky Way, trying to understand the large-scale motions of stars within our cosmic neighborhood. There is something beautiful about how Rubin's research progressed, like concentric circles expanding outward from our galactic home. First, she studied individual stars within the Milky Way, then stellar groups, then entire spiral arms, and finally, whole galaxies. Each level of observation revealed new puzzles, new questions about how gravity behaved on cosmic scales. It was only when she turned her attention to external galaxies that the true magnitude of the mystery became clear. The technology of the 1960s and 1970s allowed Rubin to do something Zwicky could never have imagined. She could measure the velocities of individual stars within distant galaxies, creating detailed rotation curves that mapped how orbital speed changed with distance from the galactic center. Night after night, she and her collaborator, Kent Ford, collected spectra from spiral galaxies, each one a cosmic fingerprint that revealed the gravitational dance occurring hundreds of millions of light years away. As Rubin's observations accumulated, a pattern emerged that was both beautiful and bewildering. Galaxy after galaxy showed the same impossible behavior. Stars in the outer regions, moving far too fast to be held by the gravity of visible matter alone. The rotation curves remained stubbornly flat when they should have been declining, indicating the presence of enormous amounts of invisible matter extending far beyond the visible edges of each galaxy. What made Rubin's work so compelling was its systematic nature. This wasn't a single anomalous observation that could be dismissed as measurement error or peculiar circumstances. Dozens, then hundreds of galaxies all told the same story. The universe contained vast quantities of matter that interacted gravitationally but remained completely invisible to all forms of electromagnetic radiation. The transition from Zwicky's cluster observations to Rubin's galactic rotation curves represents one of those beautiful moments in science when different approaches converge on the same profound truth. Zwicky had detected dark matter's influence on the largest scales, entire clusters of galaxies. Rubin revealed its presence on intermediate scales, individual galaxies, and their stellar populations. Together, their work painted a picture of a universe dominated by invisible matter on every scale where gravity was the primary organizing force. Perhaps the most remarkable aspect of these pioneering discoveries is how they emerged from pure observational astronomy. Neither Zwicky nor Rubin had sophisticated theoretical frameworks predicting the existence of dark matter. They simply looked carefully at the cosmos, measured what they saw with precision and honesty, and allowed the universe itself to reveal its secrets. Their work reminds us that sometimes the most profound discoveries come not from complex theories, but from the patient willingness to let reality speak for itself. As we drift deeper into the story of dark matter's discovery, we can almost feel the excitement and bewilderment that must have filled those observatories. Here were astronomers who had dedicated their lives to understanding the visible universe, only to discover that everything they could see represented merely the tip of a cosmic iceberg. The darkness between the stars was not empty. It was full of invisible matter, shaping the very structures they had spent their careers studying. In the quiet depths of cosmic investigation, there comes a moment when the invisible reveals itself not through direct observation, but through the subtle ways it bends and shapes the light of more distant objects. This is the story of how astronomers learned to read the universe's invisible fingerprints, using light itself as a cosmic detective to map the presence of dark matter across the vast expanses of space and time. There is something almost magical about gravitational lensing, the phenomenon that would become one of our most powerful tools for detecting dark matter. Picture light as a cosmic traveler, journeying across billions of years and trillions of miles to reach our telescopes. Along its path, this light encounters massive concentrations of matter, galaxies, galaxy clusters, and the invisible dark matter halos that surround them. According to Einstein's general relativity, these massive objects bend the fabric of space-time itself, creating cosmic lenses that focus, stretch, and distort the light of objects lying even further beyond. When astronomers first began to notice these gravitational mirages, they realized they had discovered a way to weigh the invisible universe. The degree to which background galaxies appear distorted reveals precisely how much mass lies between us and them. Not just the mass we can see in glowing stars and gas clouds, but all the mass present, including the dark matter that remains stubbornly invisible to our instruments. The beauty of gravitational lensing lies in its democratic honesty. Light doesn't discriminate between different types of matter. It responds equally to the gravitational pull of ordinary atoms and dark matter particles. This means that lensing observations provide a direct measurement of the total mass distribution in the universe, offering a cosmic census that includes both the seen and the unseen. As we drift deeper into this cosmic detective story, we encounter one of the most compelling pieces of evidence for dark matter's existence, the bullet cluster. This remarkable cosmic collision, officially cataloged as 1E Zoexec 575558, provides what many consider the smoking gun proof that dark matter is real and distinct from ordinary matter. Picture two massive galaxy clusters, each containing hundreds of galaxies embedded within vast halos of dark matter and hot gas, approaching each other across the cosmic void. When these titans collide at speeds of several million miles per hour, something extraordinary happens that reveals the different natures of visible and dark matter. The hot gas that fills the space between galaxies, visible to X-ray telescopes as glowing plasma heated to millions of degrees, slams into itself during the collision, creating shock waves and friction that slow its progress. But dark matter, with its ghostly ability to interact only through gravity, passes right through the collision, largely unaffected. Like cosmic phantoms, the dark matter halos of both clusters slide past each other with minimal disruption, carrying their embedded galaxies along for the ride. The result is a cosmic crime scene where the evidence has been neatly separated. The hot, ordinary matter, detected by X-ray observations, is found in one location, while gravitational lensing reveals that most of the mass, the dark matter, has continued onwards to a different position. There is something profoundly beautiful about this cosmic separation. In a single astronomical object, we can see the universe naturally performing an experiment that clearly distinguishes between ordinary and dark matter. The bullet cluster doesn't just suggest that dark matter exists, it shows us dark matter and ordinary matter in the act of behaving differently, providing visual proof of their distinct natures. Meanwhile, across the vast expanse of cosmic history, another type of fingerprint was being discovered in the most ancient light we can observe, the cosmic microwave background radiation. This gentle glow, the afterglow of the Big Bang itself, carries within its subtle temperature variations the imprint of dark matter's influence in the very early universe. When the universe was only 380,000 years old, a mere infant in cosmic terms, it finally cooled enough for the first atoms to form and light to travel freely through space. The pattern of tiny temperature fluctuations in this primordial light reveals the seeds of all future structure, the slight density variations that would eventually grow into galaxies, galaxy clusters, and the cosmic web itself. The exquisite beauty of these cosmic microwave background observations lies in how they reveal dark matter's earliest handiwork. The acoustic oscillations, sound waves that rippled through the primordial plasma, created a specific pattern of peaks and valleys in the temperature map. The precise locations and heights of these peaks depend critically on the relative amounts of ordinary matter, dark matter, and dark energy in the universe. It is as if the universe signed its composition on the cosmic microwave background, creating a kind of cosmic birth certificate that lists the exact ingredients present at the moment of cosmic dawn. When astronomers analyze this ancient light with instruments like the Planck satellite, they find that the signature perfectly matches what we would expect if dark matter makes up about 27% of the universe's total energy density. There is something deeply moving about how these different observational techniques, gravitational lensing, galaxy cluster collisions, and cosmic microwave background analysis, all point to the same conclusion. Like witnesses to a cosmic truth, each type of observation provides independent confirmation that our universe is dominated by forms of matter and energy that remain largely mysterious to us. Perhaps the most remarkable aspect of reading these cosmic fingerprints is how they transform absence into presence. Dark matter cannot be seen directly, but its gravitational influence is written in the bent light of distant galaxies, the separated components of colliding clusters, and the ancient patterns imprinted on the sky's oldest light. Through patient observation and careful analysis, astronomers have learned to make the invisible visible, to find the hidden through its effects on what can be seen. As we rest in contemplation of these cosmic revelations, we can appreciate how the universe itself has provided us with the tools needed to detect its hidden majority. Light, that most fundamental messenger of the cosmos, becomes our guide into the invisible realm, bending and warping to reveal the presence of matter that would otherwise remain forever beyond our perception. In the gentle realm of cosmic cartography, there exists perhaps no more ambitious undertaking than attempting to map the invisible architecture of the entire universe. Tonight, we drift into the contemplation of humanity's greatest census project, the patient, methodical effort to chart the distribution of dark matter across billions of light years and billions of years of cosmic time. Picture, if you will, the challenge that faced astronomers at the dawn of the 21st century. They had compelling evidence that dark matter existed and dominated the universe's mass budget, but understanding its detailed distribution required mapping something that could not be directly observed across scales ranging from individual galaxies to the largest structures in the cosmos. It was like trying to chart the ocean floor, using only the patterns of waves visible on the surface. The solution came through one of the most beautiful applications of gravitational lensing ever conceived, weak lensing surveys that could measure the subtle distortions of millions of distant galaxies simultaneously. Unlike the dramatic Einstein rings and multiple images created by strong gravitational lensing, weak lensing produces effects so gentle that they can only be detected through statistical analysis of vast numbers of background galaxies. There is something almost meditative about the process these surveys employ. Imagine robotic telescopes systematically photographing patch after patch of sky, each image containing thousands of distant galaxies whose light has traveled across cosmic time to reach us. In each photograph, dark matter concentrations along the line of sight create tiny distortions in the shapes of these background galaxies, stretching some into slightly more elliptical forms, creating subtle alignments where none should exist. Individual galaxy shapes are influenced by many factors beyond gravitational lensing, making any single measurement ambiguous. But when astronomers analyze hundreds of thousands, then millions of galaxy images, the random factors average out, while the systematic distortions created by dark matter emerge from the cosmic noise, like a signal gradually strengthening on a radio telescope. Through this patient statistical archaeology, the invisible universe slowly reveals its architecture. The results of these cosmic censuses have been nothing short of breathtaking. Maps of dark matter distribution across the sky reveal a universe structured like a vast cosmic web, with dense nodes connected by filaments of invisible matter stretching across hundreds of millions of light years. Where these filaments intersect, enormous clusters of galaxies have formed, their visible components highlighting the underlying dark matter scaffolding that has been there all along. Meanwhile, in the quiet depths of computer laboratories around the world, another type of cosmic exploration was taking place. Supercomputer simulations, with names like the Millennium Run, Illustrious, and Eagle, began recreating the entire history of cosmic structure formation from the Big Bang to the present day. These computational universes, containing billions of simulated dark matter particles, allowed astronomers to watch the cosmic web form and evolve over billions of years of compressed time. There is something almost godlike about these simulations, the ability to create entire virtual universes and watch them evolve, to experiment with different amounts of dark matter and dark energy, and see how cosmic structure changes in response. The Millennium Run, completed in 2005, followed the gravitational dance of over 10 billion dark matter particles across a cube of space 2 billion light years on each side, requiring months of computation on some of the world's most powerful supercomputers. The beauty of these simulations lies not just in their computational achievement, but in how closely their results match the actual universe we observe. When astronomers compare the simulated cosmic web with real observations from large galaxy surveys, like the Sloan Digital Sky Survey, the agreement is remarkable. The same filamentary structure, the same clustering patterns, the same relationship between dark matter halos and the galaxies that form within them all emerge naturally from the computer models. Yet, perhaps the most profound revelation from these cosmic censuses has been the confirmation that dark matter's influence extends across every scale where gravity dominates, from the smallest dwarf galaxies containing only a few million stars to the largest galaxy clusters spanning tens of millions of light years. The presence of dark matter halos appears universal. It is as if every luminous structure in the universe exists within an invisible cocoon of dark matter. The statistical precision of modern dark matter maps has reached extraordinary levels. Surveys like the Dark Energy Survey and the upcoming Euclid mission can measure dark matter concentrations with percentage-level accuracy across vast regions of sky. This precision allows astronomers to test theoretical predictions in unprecedented detail, checking whether the observed distribution matches what we would expect from our best models of cosmic structure formation. There is something deeply satisfying about how these various approaches to cosmic census-taking complement each other. Ground-based telescopes provide wide-area surveys that map dark matter over large volumes of space. Space-based observations offer the sharp resolution needed to study individual galaxy clusters in detail. Computer simulations provide the theoretical framework that connects observations at different scales and cosmic epochs. As we drift deeper into contemplation of this great cosmic census, we can appreciate how it represents humanity's most ambitious attempt to understand our place within the larger universe. By mapping the distribution of a dark matter, we are charting the invisible foundation upon which all visible structure rests. This enhanced gravitational pull could explain why stars in galactic suburbs move faster than expected without requiring any invisible matter at all. There is something deeply appealing about Mond's philosophical elegance. It suggests that the universe operates according to a more subtle law than we previously recognized, one that reveals itself only under the most extreme conditions of scale and time, like a musical instrument that plays different harmonies. When touched with the gentlest pressure, gravity under Mond behaves differently in the cosmic whisper zones, where accelerations are almost, but not quite, zero. Yet as we drift deeper into this alternative landscape, we encounter the beautiful complexity of scientific debate. Mond succeeds remarkably well at explaining galactic rotation curves, the very observations that first revealed the dark matter mystery. For many individual galaxies, Mond's predictions match observations with surprising precision, often better than dark matter models that require careful fine-tuning of invisible halo properties. However, the universe rarely offers simple solutions to profound mysteries. As observations expanded beyond individual galaxies to galaxy clusters and the cosmic microwave background, Mond began to struggle. The collision dynamics of the bullet cluster, where dark matter and ordinary matter appear to have separated during a cosmic crash, proves difficult to explain without invoking some form of invisible matter. The precise patterns in the cosmic microwave background seem to require the specific gravitational signatures that dark matter provides during the universe's earliest epochs. Meanwhile, other alternative theories have emerged from the fertile ground of theoretical physics. Some propose that gravity might leak into extra dimensions on cosmic scales, weakening its apparent strength and mimicking the effects we attribute to dark matter. Others suggest that the quantum vacuum itself might behave differently in the presence of matter, creating emergent gravitational effects that we misinterpret as evidence for invisible particles. There is something profoundly beautiful about this ongoing scientific dialogue. The dark matter hypothesis and modified gravity theories represent two fundamentally different ways of understanding reality. Dark matter suggests that the universe contains forms of matter beyond our current particle physics knowledge, that the cosmic inventory includes entirely new types of substance that interact only through gravity. Modified gravity theories propose that space-time itself behaves according to laws more subtle and complex than we have yet fully grasped. The scientific community's gradual embrace of dark matter over modified gravity reflects not dogma, but the patient accumulation of evidence from multiple independent observations. Galaxy rotation curves alone might be explained by either approach, but when we add gravitational lensing observations, cosmic microwave background measurements, large-scale structure surveys, and computer simulations of cosmic evolution, the dark matter hypothesis proves more successful at explaining the full range of phenomena with a single, unified framework. Yet perhaps the most remarkable aspect of this scientific debate is how it reflects the healthy skepticism that drives discovery. Even as evidence for dark matter has accumulated, researchers continue to develop and test alternative theories. Some hybrid approaches even combine elements of both perspectives, suggesting that dark matter exists, but that gravity also behaves slightly differently on cosmic scales. There is something deeply reassuring about science's willingness to question its own conclusions. The existence of alternative theories like MOND keeps dark matter researchers honest, forcing them to continually test and refine their models against new observations. Similarly, the success of dark matter models in explaining diverse cosmic phenomena challenges modified gravity theorists to develop more comprehensive alternatives. As we rest in contemplation of these competing visions, we can appreciate how they both spring from the same source: humanity's refusal to accept easy answers when the universe presents us with profound mysteries. Whether dark matter consists of exotic particles streaming invisibly through space, or whether gravity itself holds secrets we have yet to unlock, the quest for understanding drives us toward ever more precise observations and ever more sophisticated theories. Perhaps the most beautiful lesson from this ongoing debate is that the universe may be even more mysterious and wonderful than either perspective alone suggests. The cosmos has already surprised us with the existence of black holes, quantum mechanics, and cosmic acceleration. Why should we expect its deepest secrets to yield easily to our current understanding? In questioning both our theories and our observations, we remain open to discoveries that might transcend the current debate entirely, revealing truths about reality that we haven't yet learned to imagine. In the quiet depths of cosmic space, where galaxies drift like islands of light across the dark ocean of the universe, there exists an invisible architecture so fundamental that without it, none of the beauty we observe could exist. Tonight, we drift into contemplation of how dark matter shapes not just the large-scale structure of the cosmos, but the intimate details of stellar birth, galactic evolution, and the delicate dance between the seen and unseen that governs every astronomical phenomenon we observe. Picture, if you will, our own Milky Way galaxy not as the elegant spiral of stars we see in artistic representations, but as it truly exists, a relatively small collection of luminous matter embedded within a vast, roughly spherical halo of invisible dark matter. This dark matter halo extends perhaps 10 times farther from the galactic center than the visible stellar disk, creating a gravitational cocoon that holds our entire galactic family together. There is something almost maternal about these dark matter halos. They provide the gravitational embrace that keeps galaxies intact across billions of years, maintaining their structural integrity even as they rotate, collide with neighbors, and experience the disruptive influences of supernovae and stellar winds. Without this invisible scaffolding, the stars we see would have long ago dispersed into the cosmic void, their orbital velocities too high for the gravity of visible matter alone to maintain their galactic citizenship. The relationship between dark matter halos and their embedded galaxies reveals one of the most beautiful examples of cosmic symbiosis. Dark matter provides the gravitational foundation, but ordinary matter provides the substance that can radiate energy, cool, and condense into stars. This partnership began in the earliest epochs of cosmic history, when the first dark matter halos began to accumulate the hydrogen and helium that would eventually ignite as the first generation of stars. As we drift deeper into this cosmic architecture, we discover that dark matter doesn't just provide a passive gravitational container for galaxies. It actively governs the process of star formation itself. When gas clouds within dark matter halos reach sufficient density to begin collapsing under their own gravity, the dark matter's gravitational field helps determine where and when this collapse occurs. The invisible halo acts like a cosmic conductor, orchestrating the symphony of stellar birth. According to gravitational rhythms we are only beginning to understand, the mass of a dark matter halo determines many fundamental properties of its galaxy. Larger, more massive halos can hold onto their gas more effectively, allowing for prolonged periods of star formation. Smaller halos may lose their gas to energetic stellar winds and supernova explosions, shutting down star formation prematurely. This connection between invisible dark matter mass and visible stellar populations creates a cosmic hierarchy where halo properties ultimately determine galactic destiny. There is something almost breathtaking about the precision of this relationship. Computer simulations reveal that galaxies and their dark matter halos grow together in a delicate balance, each influencing the other's evolution through gravitational feedback mechanisms that operate across billions of years. When galaxies form stars too rapidly, the energy released can heat and expel gas from the halo. When star formation proceeds too slowly, gas continues to accumulate, eventually triggering new bursts of stellar birth. The structure within dark matter halos themselves tells a story of cosmic evolution written in gravitational dynamics. These halos are not uniform, smooth distributions of invisible matter, but complex systems with dense central regions, extended outer reaches, and substructures created by the gravitational influence of smaller halos that have merged over cosmic time. Each galaxy's dark matter halo carries within its invisible architecture a history of all the cosmic encounters and mergers that shaped its growth. Perhaps the most remarkable aspect of dark matter's cosmic architecture is how it creates diversity within unity. While all galaxies exist within dark matter halos, the specific properties of each halo, its mass, concentration profile, and merger history help determine whether a galaxy becomes a massive spiral like our Milky Way, a giant elliptical containing trillions of stars, or a tiny dwarf galaxy with only a few million stellar inhabitants. The relationship between visible and invisible matter also reveals itself in the phenomenon of galactic rotation curves that we explored earlier. The flat rotation curves observed in spiral galaxies represent a perfect balance between the gravitational pull of dark matter and the centrifugal force of orbital motion. This balance is so precise that stars maintain stable orbits for billions of years, allowing complex chemical evolution and the gradual enrichment of galactic environments with heavy elements forged in stellar cores. Meanwhile, across the vast expanses between galaxies, dark matter continues to shape cosmic architecture through its role in the ongoing process of large-scale structure formation. Dark matter halos don't exist in isolation. They are connected by filaments of invisible matter that channel gas and smaller galaxies along cosmic highways, facilitating the growth and evolution of galactic systems across cosmic time. There is something deeply moving about recognizing our place within this invisible architecture. Every star we see in the night sky, including our own sun, owes its existence to the patient work of dark matter in gathering the raw materials for stellar birth. The elements in our bodies were forged in stellar cores that could only exist because dark matter halos provided the gravitational stages where cosmic chemistry could unfold. The ongoing coevolution of dark matter, halos, and their galaxies continues today, a slow cosmic dance that will persist for billions of years into the future. Our Milky Way's dark matter halo continues to accrete smaller structures, occasionally capturing dwarf galaxies and incorporating them into our galactic system. This process of hierarchical growth, driven by dark matter's gravitational influence, represents one of the fundamental organizing principles of cosmic evolution. As we rest in contemplation of this invisible architecture, we can appreciate how dark matter serves as both foundation and conductor for the cosmic symphony of structure formation. Its gravitational influence operates across scales, from individual galaxies to the largest structures in the universe, creating the framework within which all astronomical beauty can emerge and evolve. In learning about dark matter's architectural role, we discover that the invisible realm is not separate from the visible universe we love, but intimately woven into every aspect of cosmic evolution and stellar birth. In the gentle flow of cosmic time, there was once an epoch so profound in its darkness that no star had ever shone, no galaxy had ever sparkled, and no light of any kind illuminated the vast expanse of space. Tonight, we drift into contemplation of this most mysterious period in our universe's history, the cosmic dark ages, when only dark matter stirred in the primordial blackness, patiently preparing the stage upon which all future light would dance. Picture, if you will, the universe roughly 400,000 years after the Big Bang, at the moment when the cosmos finally cooled, enough for the first atoms to form. This event, known as recombination, marks one of the most important transitions in cosmic history. For the first time since the universe began, electrons and protons could combine to create neutral hydrogen atoms, and light could travel freely through space without being scattered by charged particles. The universe became transparent, allowing the cosmic microwave background radiation to begin its journey toward our telescopes today. Yet, this moment of cosmic transparency paradoxically ushered in the darkest period the universe would ever know. With no sources of light beyond the fading afterglow of the Big Bang itself, space entered a phase of absolute darkness that would persist for hundreds of millions of years. There were no stars to ignite, no galaxies to spiral, no quasars to blaze across cosmic distances. The universe existed in a state of perfect, pristine blackness, broken only by the invisible dance of dark matter. There is something almost meditative about contemplating this cosmic dark age. In our modern universe, space seems filled with light. Stars shine from every galaxy. Quasars beam across billions of light years. And even the space between galaxies glows faintly with scattered starlight. But during the Dark Ages, space was truly empty of illumination, a vast cathedral of darkness where only gravity could whisper its subtle influences across the expanding void. Yet this darkness was not emptiness, it was potential. Like a garden lying fallow in winter, gathering strength for spring's eventual flowering, the dark universe was accumulating the ingredients for all future beauty. Dark matter, freed from the electromagnetic interactions that had prevented ordinary matter from clumping during the universe's hot, dense early phases, began its patient work of gravitational sculpture. The invisible dark matter, particles, streaming through space at speeds determined by the cosmic expansion, gradually began to slow their motion and collect into the first gravitational wells. These primordial dark matter halos, much smaller and more numerous than the massive structures we observe today, created the seeds of cosmic architecture. Within their gravitational embrace, ordinary matter, primarily hydrogen and helium gas, began to accumulate, cooling and condensing as it fell into the invisible potential wells that dark matter had carved in space-time. As millions of years passed in darkness, something wonderful was happening. The interplay between dark matter's gravitational pull and ordinary matter's ability to radiate energy away created conditions that had never existed before in the universe's history. Gas clouds within dark matter halos could cool to temperatures just above absolute zero, reaching densities that approach the threshold needed for gravitational collapse and the ignition of the first stars. There is something almost musical about this slow preparation for cosmic dawn. Dark matter halos of different masses created gravitational symphonies of different tones. Larger halos could hold on to their gas more effectively, creating the conditions for massive star formation. Smaller halos provided gentler gravitational environments where smaller, longer-lived stars might eventually form. The invisible architecture of dark matter was composing the score for the cosmic light show that was yet to come. The transition from cosmic darkness to cosmic light represents one of the most profound phase changes in the history of the universe. When the first stars finally ignited, roughly 200 million years after the Big Bang, they didn't simply add illumination to a dark universe. They fundamentally transformed the nature of cosmic evolution itself. These first stellar furnaces began producing heavy elements beyond hydrogen and helium, creating the atomic diversity that would eventually enable the formation of planets and life. Yet even this cosmic dawn depended entirely on the invisible scaffolding that dark matter had constructed during the Dark Ages. The first stars formed within dark matter halos, their nuclear fires fed by gas that had been gravitationally gathered by invisible matter. Without dark matter's patient work during the Dark Ages, the universe would have remained a smooth, expanding sea of gas, never developing the density contrasts needed for stellar birth. The end of the cosmic Dark Ages came not with a single moment of illumination, but with a gradual dawn that spread across the universe over hundreds of millions of years. As the first stars lived their brief, brilliant lives and died in spectacular supernovae, they began a process called reionization, breaking apart the neutral hydrogen atoms that had formed during recombination and filling space with a diffuse plasma of charged particles. Perhaps the most beautiful aspect of the cosmic Dark Ages is how they represent the universe's patient preparation for complexity. During this seemingly empty period, dark matter was quietly arranging the gravitational foundation for everything that would follow. Every galaxy we see today, every star in the night sky, every planet orbiting those stars, traces its ultimate origins to structures that began forming in the invisible darkness of this primordial epoch. As we rest in contemplation of these cosmic Dark Ages, we can appreciate how they reveal something profound about the nature of creation itself. Sometimes, the most important work happens in silence, in darkness, in periods when nothing visible seems to be occurring. The universe's greatest architectural project, the formation of cosmic structure, began not with light and drama, but with the patient, invisible accumulation of dark matter in the cosmic void. The Dark Ages remind us that emptiness and darkness are not the same as absence or inactivity. In what appeared to be a perfectly quiet, perfectly dark universe, the seeds of all future beauty were being planted by invisible hands. The cosmic Dark Ages represent not just a period in the universe's history, but a testament to the creative power of patience, preparation, and the gentle persistence of gravitational forces working across vast expanses of time and space. In the gentle realm of cosmic evolution, where time flows like a slow river carrying galaxies through billions of years of change, we discover that each stellar system exists not as an isolated island, but as part of a vast, interconnected ecosystem shaped by the invisible presence of dark matter. Tonight, we drift into contemplation of how this ghostly substance orchestrates the life cycles of galaxies, governs their interactions, and determines the fate of entire stellar communities across cosmic time. Picture, if you will, a galaxy not as a static collection of stars frozen in space, but as a living, breathing organism that grows, evolves, and interacts with its cosmic environment. Like a tree in a forest, each galaxy exists within a larger ecosystem where its development depends not only on its own internal processes, but on its relationships with neighbors, its access to cosmic resources, and the invisible dark matter scaffolding that connects all galactic communities across vast distances. The ecological metaphor becomes even more compelling when we consider how dark matter governs the flow of cosmic resources. Just as rivers channel nutrients through terrestrial ecosystems, streams of dark matter direct the flow of gas, the raw material for star formation, along invisible filaments that connect galaxies across millions of light years. Galaxies positioned at the intersections of these dark matter highways have access to continuous supplies of fresh gas, enabling prolonged periods of star formation and sustained galactic growth. There is something almost breathtaking about the role dark matter plays in galactic collisions, cosmic events so spectacular that they reshape entire stellar systems over hundreds of millions of years. When two galaxies approach each other across the cosmic void, their dark matter halos begin interacting long before their stars come close to touching. The invisible halos spiral around each other in a gravitational dance that can persist for billions of years, slowly sapping orbital energy until the galaxies finally merge into a single, larger system. During these cosmic collisions, dark matter behaves like a patient choreographer, orchestrating events across scales that span from individual stellar orbits to the global restructuring of galactic architecture. While the stars within colliding galaxies rarely collide directly, they are separated by distances so vast that physical contact is almost impossible. The dark matter halos merge more smoothly, creating new gravitational environments that profoundly affect stellar motion and star formation patterns. The most famous example of galactic collision dynamics is unfolding in our cosmic neighborhood right now as the Andromeda Galaxy approaches our Milky Way for a rendezvous scheduled roughly 4.5 billion years from now. Computer simulations reveal how this cosmic collision will unfold. First, the dark matter halos of both galaxies will begin to overlap and interact, creating tidal forces that will gradually disrupt the orderly rotation of both stellar disks. Over the course of 1 billion years or more, the two galaxies will dance around each other multiple times before finally settling into a single, massive elliptical galaxy. Yet perhaps the most poignant aspect of galactic ecosystems involves the fate of dwarf galaxies, the small, faint stellar communities that orbit larger galaxies like cosmic satellites. These galactic minnows, containing anywhere from a few million to a few billion stars, provide some of the most compelling evidence for dark matter's existence, while simultaneously illustrating the delicate balance that governs cosmic ecosystems. Dwarf galaxies are dominated by dark matter to an even greater degree than their larger cousins in the smallest dwarf galaxies. Dark matter outweighs ordinary matter by ratios of hundreds to one, creating stellar systems where the visible components represent merely the tip of an invisible iceberg. This extreme dark matter dominance makes dwarf galaxies both valuable laboratories for studying dark matter physics and tragic examples of cosmic vulnerability. The ecosystem dynamics become particularly poignant when we consider the process of galactic cannibalism, the gradual consumption of smaller galaxies by larger ones. As dwarf galaxies orbit within the dark matter halos of massive galaxies like our Milky Way, they experience tidal forces that slowly strip away their outer stars and even their dark matter. Over cosmic time, these satellite galaxies are gradually dismantled, their stellar populations dispersed into extended streams that continue to orbit the parent galaxy like cosmic ghost trails. There is something deeply moving about observing these stellar streams in our own galactic neighborhood. The Sagittarius Stream, visible as a faint river of stars wrapping around our galaxy, represents the ongoing destruction of a dwarf galaxy that has been orbiting the Milky Way for billions of years. Each time this small galaxy passes through our galactic disk, tidal forces strip away more of its stars, creating a stellar breadcrumb trail that maps its orbital history across cosmic time. Yet this process of galactic consumption is not merely destructive. It also represents a form of cosmic recycling that enriches the ecosystems of larger galaxies. The stars torn from disrupting dwarf galaxies carry with them heavy elements forged in their original stellar communities. When these stars eventually complete their life cycles within their new galactic homes, they enrich the interstellar medium with metals that become available for future generations of star formation. The study of galactic ecosystems also reveals how dark matter influences the chemical evolution of stellar communities. Galaxies embedded in more massive dark matter halos can retain their gas more effectively against the disruptive effects of stellar winds and supernova explosions. This enhanced gas retention allows for more prolonged star formation and more complete chemical enrichment, creating environments where complex chemistry can develop over cosmic time. As we drift deeper into contemplation of these galactic ecosystems, we begin to appreciate how dark matter serves not just as gravitational scaffolding, but as an active participant in the cosmic food web. The invisible substance governs the flow of resources between galactic communities, determines which stellar systems will thrive and which will be consumed, and shapes the chemical evolution that eventually enables the formation of planets and the emergence of life. Perhaps the most remarkable aspect of galactic ecosystems is how they demonstrate the interconnected nature of cosmic evolution. No galaxy evolves in isolation. Each stellar system is influenced by its dark matter environment, its position within the cosmic web, and its relationships with neighboring galaxies. The ecological perspective reveals the universe not as a collection of separate objects, but as an integrated system where the fate of each component depends on the health and evolution of the whole. As we rest in contemplation of these cosmic ecosystems, we can appreciate how our own existence depends on the successful evolution of galactic communities over billions of years. The elements in our bodies were forged in stars that lived and died within galactic ecosystems shaped by dark matter. Our solar system, formed from material enriched by countless generations of stellar evolution within the Milky Way's gravitational embrace. In understanding galactic ecosystems, we discover our own deep connections to the invisible architecture that governs cosmic evolution on the grandest scales. In the quiet depths of scientific perseverance, where human curiosity encounters the universe's most elusive secrets, there unfolds perhaps the most ambitious treasure hunt in history. Tonight, we drift into contemplation of the ongoing quest to directly detect dark matter, a search that has driven researchers to the deepest places on Earth and the farthest reaches of space, armed with instruments so sensitive they can detect the whisper of a single atomic nucleus disturbed by a cosmic ghost. Picture, if you will, the underground cathedrals where this cosmic vigil takes place, thousands of feet beneath the Earth's surface. In abandoned mines and purpose-built laboratories, scientists have created sanctuaries of silence where the most sensitive detectors ever conceived wait patiently for the almost impossible, the direct collision between a dark matter particle and ordinary matter. These subterranean temples of science exist in a realm of near-perfect stillness, shielded from the cosmic ray shower that constantly bombards the surface, protected from the electromagnetic noise of our technological civilization. In the Gran Sasso laboratory beneath Italy's Apennine Mountains, the xenon experiment maintains its patient watch. Picture tanks containing hundreds of kilograms of liquid xenon, cooled to temperatures that would freeze the air we breathe, monitored by systems so precise they can distinguish between different types of particle interactions based on the subtle patterns of light and electrical charge they create. There is something almost monastic about these underground chambers, where scientists descend daily to tend instruments that might register only a handful of potential dark matter interactions per year. Meanwhile, across the Atlantic, the Elux Zeppelin detector nestles nearly a mile underground in the former Homestake gold mine in South Dakota. This instrument, housed within concentric spheres of shielding materials, represents the culmination of decades of technological development. Its liquid xenon target, surrounded by layers of lead and plastic designed to block unwanted radiation, exists in conditions of sensitivity so extreme that the entire detector must be isolated from vibrations, temperature fluctuations, and electromagnetic interference that would be imperceptible to any other scientific instrument. There is something beautifully paradoxical about these dark matter detectors. They represent some of humanity's most sophisticated technology, yet they are designed to detect something that barely interacts with the physical world. They are marvels of engineering precision, built to catch cosmic phantoms that might pass through the entire Earth without disturbing a single atom. The patient dedication required for this research challenges our normal expectations of scientific timescales. Experiments run for years or even decades, accumulating data grain by grain, waiting for signatures that may never come. Yet the hunt for dark matter extends far beyond these underground sanctuaries. High above Earth's atmosphere, space-based observatories are mapping the invisible universe with unprecedented precision. The Euclid Space Telescope, launched as humanity's most ambitious dark matter surveyor, is creating the most detailed map of cosmic structure ever attempted, measuring the subtle gravitational lensing effects of dark matter across billions of galaxies. From its vantage point beyond Earth's atmospheric distortions, Euclid can detect gravitational lensing with sensitivity that would have seemed miraculous just decades ago. By measuring the tiny distortions that dark matter creates in the shapes of distant galaxies, this cosmic cartographer is revealing the three-dimensional architecture of the invisible universe across vast expanses of space and time. Each photograph contains thousands of galaxies, each galaxy's slightly distorted shape, providing a piece of evidence for the dark matter structures that lie between us and the cosmic horizon. Meanwhile, the Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, promises to push dark matter detection to even greater precision. This instrument will survey larger areas of sky with greater sensitivity than any previous mission, potentially detecting dark matter structures too subtle for current ground-based telescopes to resolve. It represents the next generation of cosmic archaeology, designed to read the gravitational signatures that dark matter has written across the history of cosmic structure formation. Perhaps the most exciting frontier in dark matter detection lies in the development of entirely new detection technologies, quantum sensors capable of detecting disturbances smaller than any classical instrument could measure, offer the possibility of detecting dark matter interactions that current detectors would miss entirely. Superconducting materials cooled to temperatures approaching absolute zero might reveal dark matter signatures through changes in their quantum properties, so subtle that they challenge the fundamental limits of measurement. The search is also expanding into new theoretical territories, axion detectors, designed to catch these hypothetical ultralight particles as they interact with strong magnetic fields, represent a completely different approach to dark matter detection. These experiments seek to detect dark matter not through nuclear collisions, but through the conversion of axions into photons in the presence of powerful magnetic fields, a quantum mechanical process so delicate that it occurs at rates that would challenge even our most sensitive instruments. There is something deeply moving about the international collaboration that characterizes modern dark matter research. Scientists from dozens of countries work together, sharing data, comparing results, and collectively pushing the boundaries of what is technically possible. Underground laboratories in Italy communicate with detectors in South Dakota. Space-based missions complement ground-based observations, and theoretical physicists work closely with experimental teams to interpret the faintest signals that might emerge from years of data collection. The hunt for dark matter also drives innovation far beyond astronomy and particle physics. The ultra-sensitive detectors developed for dark matter research have found applications in medical imaging, nuclear security, and quantum computing. The computational methods used to analyze dark matter data contribute to advances in artificial intelligence and machine learning. In searching for the invisible majority of our universe, scientists create new technologies that benefit human civilization in ways that extend far beyond cosmology. As we rest in contemplation of this ongoing quest, there is something profoundly hopeful about humanity's determination to understand the invisible foundations of reality. The hunt for dark matter represents one of our species' most ambitious intellectual challenges, an attempt to detect something that might interact with our instruments only rarely, if at all. It requires patience that spans careers, international cooperation on unprecedented scales, and technological innovation that pushes the limits of what is physically possible. Perhaps the most beautiful aspect of this continuing hunt is how it connects the largest and smallest scales of physical reality in underground laboratories and orbiting telescopes. Researchers probe for particles that shape galactic evolution and cosmic structure formation. They seek to understand how quantum interactions in the early universe created the gravitational scaffolding upon which all subsequent cosmic beauty depends. Whether dark matter consists of exotic particles beyond our current understanding or represents new physics we have yet to imagine, the search continues to reveal new aspects of the universe's profound mystery and beauty. In the gentle intimacy of our local cosmic environment, where Earth orbits the Sun and our solar system drifts through the spiral arms of the Milky Way, there exists a presence so subtle yet so pervasive that it touches every moment of our existence without our awareness. Tonight, we drift into contemplation of dark matter not as a distant cosmological concept, but as an immediate reality that flows through our cosmic neighborhood, through our planet, and through our very bodies at this very moment. Picture, if you will, our Milky Way galaxy as it truly exists, not merely the elegant spiral of stars visible in astronomical photographs, but as a vast system where visible matter represents only about 1/6 of the total mass. We live within the gravitational embrace of a dark matter halo that extends perhaps 10 times farther from the galactic center than the visible stellar disk, creating an invisible cocoon that holds our entire galactic community together across the cosmic eons. This dark matter halo is not uniform or static, but structured and dynamic, shaped by billions of years of gravitational evolution. Computer simulations reveal it to be filled with substructures, smaller clumps, and streams of dark matter that trace the orbital histories of ancient mergers and interactions. Our solar system moves through this invisible landscape like a ship sailing through cosmic currents we cannot directly perceive, yet which influence the large-scale motions of every star in our galactic neighborhood. There is something almost musical about our solar system's journey through the galaxy's dark matter halo. We orbit the galactic center once every 220 million years, rising and falling through the galactic disk in a gentle oscillation that takes us roughly 70 light years above and below the midplane during each orbit. As we travel this cosmic path, we encounter varying densities of dark matter, sometimes sailing through regions where it flows more sparsely, other times passing through streams and concentrations left behind by ancient gravitational interactions. The dark matter density in our local solar neighborhood amounts to roughly 1 proton's worth of mass per cubic centimeter of space, a density so low it approaches the definition of a perfect vacuum by terrestrial standards. Yet even this whisper-thin presence translates to approximately 300,000 particles of dark matter within every cubic meter of space, including the space occupied by your body. As you listen to these words, consider the profound intimacy of this cosmic companionship. At this very moment, dark matter particles are streaming through you at velocities of several hundred kilometers per second, speeds that would carry them from New York to Los Angeles in less than 20 seconds. These cosmic travelers, some of which may have been journeying through space since shortly after the Big Bang, pass through every atom in your body, through every cell, through every thought, without disturbing so much as a single electron in their passage. The flow of dark matter through our solar system creates what astronomers call a dark matter wind, a directional preference in the particle's motion caused by our solar system's movement through the galaxy's rotating dark matter halo. This wind changes direction and intensity as Earth orbits the Sun, creating seasonal variations in the dark matter flux that passes through our planet. During certain times of the year, Earth moves with the dark matter wind. During others, we move against it, creating subtle changes in the rate at which these invisible particles pass through terrestrial dark matter detectors. There is something deeply poignant about Earth's relationship with this invisible cosmic environment. Our planet, with its protective magnetic field and substantial mass, provides no barrier whatsoever to dark matter's passage. The same particles that stream through the vacuum of interplanetary space continue their journey through Earth's crust, mantle, and core without any measurable interaction. In this sense, our world exists in a state of perfect transparency to the dark matter ocean in which it swims. Yet this transparency does not mean irrelevance. The gravitational influence of dark matter in our cosmic neighborhood contributes to the large-scale dynamics that have shaped our solar system's evolution over billions of years. The spiral density waves that create the Milky Way's distinctive arm structure, the stellar motions that brought our Sun into its current galactic orbit, and even the subtle gravitational perturbations that may influence cometary orbits in the outer solar system. All of these phenomena occur within the context of our galaxy's dark matter architecture. The search for dark matter in our immediate cosmic vicinity has led to some of the most sensitive physics experiments ever attempted. The underground detectors we explored earlier are specifically designed to catch dark matter particles from our local galactic environment as they pass through terrestrial laboratories. Each potential detection event represents a cosmic coincidence of almost unimaginable rarity. A single dark matter particle, having traveled perhaps billions of years through space, finally interacting with a xenon nucleus in a detector tank buried beneath tons of rock and shielding. Perhaps the most remarkable aspect of dark matter in our cosmic neighborhood is how it connects us to the larger universe. The same invisible particles that helped shape the formation of our galaxy, that provided the gravitational scaffolding for stellar birth in our spiral arm, that may have influenced the dynamics of the molecular cloud from which our solar system formed, continue to flow through our local space and through our bodies today. We are immersed in a cosmic medium that links us directly to the largest scales of structure formation. There is something profoundly calming about recognizing our place within this invisible cosmic current. As we rest here on Earth, orbiting our star, traveling through our galaxy, we are also embedded within streams of dark matter that connect us to the cosmic web itself. We are not separate from the universe's invisible majority. We are swimming within it, carried along by gravitational currents that operate on scales both intimate and cosmic. The future of dark matter research in our cosmic neighborhood holds exciting possibilities. New generations of detectors may finally achieve the sensitivity needed to directly detect the dark matter particles flowing through our solar system. Space-based experiments might map dark matter substructures in our galactic vicinity with unprecedented precision. Some scientists even speculate about the possibility of using dark matter interactions for communication or navigation across cosmic distances, though such technologies remain far beyond our current capabilities. As we drift deeper into contemplation of our cosmic neighborhood's invisible population, we can appreciate how dark matter serves as a constant reminder of our connection to the larger universe. Every breath we take occurs within an ocean of invisible particles that have witnessed the entire history of cosmic structure formation. Every step we take carries us through dark matter streams that may have formed billions of years ago in the gravitational collapse of primordial density fluctuations. In understanding dark matter's presence in our cosmic neighborhood, we discover that we have never been alone. We have always been accompanied by invisible companions that connect us to the deepest mysteries of cosmic existence. In the gentle realm of human contemplation, where scientific discovery meets the deeper questions of existence and meaning, dark matter presents us with perhaps the most profound philosophical challenge of our cosmic age. Tonight, we drift into reflection on what the invisible majority of our universe teaches us about the nature of knowledge itself, the limits of human perception, and the beautiful humility that comes with recognizing how much of reality remains beyond our direct experience. Picture, if you will, the philosophical earthquake that dark matter has created in our understanding of reality. For most of human history, we operated under the reasonable assumption that the universe consisted primarily of what we could observe: stars, planets, galaxies, and the various forms of matter and energy that interact with light and therefore with our instruments. The discovery that roughly 85% of all matter exists in forms we cannot directly perceive fundamentally challenges this assumption, forcing us to confront the possibility that reality extends far beyond the boundaries of our senses. There is something deeply humbling about dark matter's hidden nature. It suggests that the universe we experience through sight, touch, and our most sophisticated instruments represents merely a small fraction of what actually exists. This realization echoes ancient philosophical traditions that have long suspected that the world we perceive directly is not the whole truth about reality. From Plato's cave allegory to Kant's distinction between phenomena and noumena, dark matter provides a concrete, scientific example of how the apparent and the real can diverge in profound ways. The implications extend beyond simple humility about our knowledge. Dark matter forces us to reconfront fundamental questions about the relationship between observation and existence. If something can be completely undetectable, yet still profoundly influence the world we observe, what does this mean for our understanding of causation, presence, and reality itself? We are asked to accept that the most important forces shaping our cosmic environment may be precisely the ones we cannot directly experience. As we drift deeper into these philosophical waters, we encounter questions about the nature of scientific knowledge itself. Dark matter was discovered not through direct observation, but through its effects on things we could observe. This represents a profound shift in how science approaches the study of reality. From direct empiricism toward a more subtle form of inference based on indirect evidence. We have learned to detect presence through absence, to map the invisible through its influence on the visible. This shift has implications that extend far beyond astronomy and physics. In accepting dark matter's reality based on gravitational effects alone, we acknowledge that some of the most fundamental aspects of reality may be accessible only through inference, interpretation, and mathematical modeling rather than direct observation. This challenges traditional empiricist philosophies that emphasize direct sensory experience as the foundation of knowledge, suggesting instead that reality is more subtle and indirect than our everyday experience would suggest. The philosophical implications become even more profound when we consider what dark matter teaches us about the relationship between complexity and perception. The universe has arranged itself in such a way that its most abundant constituents remain invisible to the very consciousness that has evolved to study it. This creates a kind of cosmic irony. The universe's capacity for self-understanding through human consciousness may be fundamentally limited by the hidden nature of most of what exists. Yet there is also something deeply beautiful about this limitation. Dark matter reminds us that mystery is not a temporary condition to be solved by better instruments or more sophisticated theories, but may be a fundamental feature of reality itself. The universe appears to be constructed in such a way that complete knowledge, perfect observation, and total understanding may be impossible in principle. This is not a failure of science, but a profound truth about the nature of existence. The discovery of dark matter also raises fascinating questions about consciousness and cosmic evolution. If the universe is dominated by forms of matter that do not interact electromagnetically, what does this mean for the emergence of consciousness, which seems to depend on electromagnetic processes in the brain? Are we, as conscious beings, capable of contemplating dark matter's existence, somehow special in our ability to perceive and understand electromagnetic phenomena? Or might there be forms of consciousness or information processing that operate through purely gravitational or other non-electromagnetic interactions? There is something almost mystical about contemplating our relationship to dark matter. We are made of atoms that were forged in stars, which themselves could only exist because dark matter provided the gravitational scaffolding for their formation. Yet the dark matter that enabled our existence remains forever beyond our direct experience. We are children of cosmic processes we cannot fully perceive, products of an invisible architecture that shapes everything we see and touch and love. The philosophical implications of dark matter extend to questions about technological possibility and cosmic communication. If the universe is dominated by matter that interacts only through gravity, what are the ultimate limits to technological development? Could advanced civilizations learn to manipulate dark matter directly, gaining access to the universe's dominant component? Or are we forever destined to remain conscious islands in a sea of invisible matter, connected to the cosmic majority only through the subtle pull of gravity? Perhaps the most profound philosophical implication of dark matter is what it suggests about the relationship between knowledge and wonder. Rather than diminishing the mystery of existence, scientific discovery has revealed that the universe is far stranger and more mysterious than we ever imagined. Dark matter doesn't solve cosmic puzzles. It reveals that the puzzles are deeper and more wonderful than we knew. There is something profoundly comforting about this cosmic humility. In a world where we often feel we have mapped and measured everything, dark matter stands as a gentle reminder that reality is far larger, far stranger, and far more beautiful than our current understanding can encompass. It suggests that the universe will always hold wonders beyond our comprehension, mysteries that will continue to inspire and challenge future generations of scientists and philosophers. As we rest in contemplation of these philosophical depths, we can appreciate how dark matter transforms our relationship to cosmic existence. We are not observers standing outside the universe looking in, but participants embedded within an invisible majority that shapes every aspect of our existence. The humility this engenders is not discouraging, but liberating. It frees us from the impossible burden of complete understanding and allows us to embrace wonder as a fundamental aspect of cosmic consciousness. In the gentle twilight of our cosmic journey together, as we draw our contemplation of dark matter toward its quiet close, we find ourselves standing at the edge of a profound realization that transforms everything we thought we understood about existence itself. Tonight, we rest in the ultimate recognition that we live not just in a universe, but in a cosmic iceberg where everything we can see, touch, and directly experience represents merely the visible tip of an infinitely deeper reality. Picture, if you will, the totality of human experience across all of history. Every star observed by ancient astronomers, every galaxy mapped by modern telescopes, every planet discovered orbiting distant suns, every nebula glowing in the depths of space. Now imagine that all of this visible splendor, everything that has ever caught the light or sparked the imagination, represents just 15% of what actually exists. The remaining 85% surrounds us, supports us, shapes us, yet remains forever beyond the reach of our eyes. There is something almost breathtaking about this realization. We have spent millennia developing increasingly sophisticated ways to see, from the first crude telescopes to the most sensitive space-based observatories, from simple photographic plates to digital detectors that can capture individual photons after their billion-year journey across cosmic space. Yet all of this magnificent technological development, all of this expansion of human perception has revealed only the smallest fraction of what surrounds us. The invisible majority that we call dark matter is not separate from our experience. It is the very foundation upon which all experience rests. The calcium in our bones, formed in the nuclear furnaces of ancient stars, exists only because dark matter first gathered the cosmic ingredients for stellar birth. The oxygen we breathe, forged in the hearts of massive stars that lived and died before our solar system formed, was created in stellar environments that could only exist within the gravitational embrace of dark matter halos. As we drift into this final contemplation, we can appreciate how dark matter reveals the universe as a masterpiece of invisible artistry, like a magnificent cathedral where the most essential structural elements remain hidden within walls and foundations. The cosmos builds its visible beauty upon invisible foundations. Every spiral galaxy maintains its graceful arms because dark matter provides the gravitational architecture that guides stellar motions across billions of years. Every galaxy cluster holds together across vast distances because invisible matter supplies the gravitational glue that prevents cosmic expansion from tearing these structures apart. The beauty of this invisible foundation lies not just in its structural necessity, but in its perfect integration with everything we can perceive. Dark matter doesn't compete with ordinary matter for cosmic importance. It enables ordinary matter to achieve its full potential for complexity and beauty. Without dark matter's patient, gravitational guidance, the atoms that eventually became stars would never have found each other across the expanding void. The elements that make planets possible, that enable the chemistry of life, that allow consciousness to emerge and contemplate its own existence, all trace their ultimate origins to processes that were enabled by invisible matter. There is something profoundly moving about recognizing our intimate connection to this cosmic invisibility. As you rest here tonight, dark matter particles are flowing through you at speeds that would carry them across continents in seconds. These cosmic travelers, some of which may have been journeying since the universe's first moments, share your space without disturbing your atoms, creating a form of communion between the seen and unseen that operates beneath the threshold of perception. Yet this communion is not merely poetic. It is fundamental to our existence. We are not accidentally embedded within dark matter's invisible ocean. We are necessarily embedded within it. Our solar system's stable orbit around the galactic center, our galaxy's structural integrity across cosmic time, the very existence of the heavy elements that make terrestrial planets, and biological complexity possible. All of these depend on the gravitational architecture that dark matter provides. The philosophical implications ripple outward like waves from a stone dropped in still water. If the universe is majoritarily invisible, what does this mean for consciousness, which seems to be the cosmos's attempt to understand itself? Are we, as thinking beings, capable of contemplating dark matter's existence, somehow representing the universe's effort to perceive its own hidden nature? Through human consciousness, does the invisible universe finally find a way to contemplate its own existence? Perhaps the most beautiful aspect of dark matter's invisible foundation is how it transforms our understanding of cosmic citizenship. We are not merely inhabitants of a planet orbiting a star in one galaxy among billions. We are participants in a cosmic community that extends far beyond what we can directly perceive. The invisible majority that surrounds us connects every atom in our bodies to the largest structures in the universe, creating a web of relationship and interdependence that spans from the quantum scale to cosmic horizons. There is something deeply calming about accepting our place within this invisible majority. Rather than making us feel small or insignificant, dark matter's pervasive presence suggests that we are intimately connected to the cosmic architecture that shapes everything. We are not separate from the universe's hidden depths. We are expressions of those depths, temporary configurations of complexity that have emerged from the invisible foundations of cosmic evolution. As our journey through dark matter's mysteries draws to its gentle close, we can rest in the recognition that mystery itself is not a problem to be solved, but a truth to be celebrated. The universe has revealed itself to be far stranger, far more mysterious, and far more beautiful than our ancestors ever dared to imagine. In discovering that most of reality remains invisible to us, we have not encountered a limitation of science, but a profound truth about the nature of existence itself. The invisible force that holds galaxies together also holds us, not just gravitationally, but spiritually, intellectually, and emotionally. We are children of processes we cannot directly perceive, yet which we can understand through patient observation, careful reasoning, and the profound human capacity for wonder. In learning about dark matter, we have learned about ourselves and our place in a cosmos that is forever larger, forever stranger, and forever more mysterious than we can fully comprehend. And perhaps that is the most beautiful truth of all, that we exist within a universe sophisticated enough to hide most of itself from direct observation, yet generous enough to reveal its secrets to patient, curious minds willing to look carefully at the visible world and infer the presence of invisible wonders beyond. Dark matter doesn't just hold galaxies together, it holds the promise that reality will always exceed our expectations, that mystery will always beckon beyond the edges of knowledge, and that the universe will continue to surprise and delight us across all the eons yet to come. In this gentle recognition, we can finally rest, knowing that we are forever held in the invisible embrace of cosmic forces that enable our existence, support our contemplation, and connect us to the deepest mysteries of space and time. The dark matter that surrounds us is not separate from us. It is the silent foundation upon which all our cosmic dreams are built.